I'll start over. So hello everyone, welcome to EEEE Lecture number 41A. So last time we have discussed about the construction, the working principle of the transformer, and also we have seen the difference between a primary and a secondary transformer, and we have discussed about, we have derived uh, the EMF equation of the transformer. Today we are going into more details of a practical transformer. So in a practical transformer, we have something called as a copper transformer losses. So write down the heading transformer losses. So the two primary losses which are occurring in a transformer are, in a practical transformer, are copper loss and iron loss. So here I should have written, in a practical transformer are copper loss and iron loss. Now what is a copper loss? Now let's see this diagram in more details. So here this is my symbol of a transformer. Okay, let's say a practical transformer. It is made up of primary and secondary windings. Now this primary and secondary windings are made up of copper wires. Now whenever a copper wire is wound around, it behaves as inductive. But we have a resistance also associated with it, right? So there is some winding resistance. And whenever there is a resistance, there is a I square R loss, which is the copper loss. Okay, so here let me remind you, E1 is V1 is my primary voltage, E1 is my self-induced EMF, I1 is the primary current, N1 and N2 are number of turns in the primary and secondary, E2 is the mutually induced EMF, I2 is the secondary current, V2 is the secondary voltage. Okay, so in a transformer the windings are not ideal. Every winding has some resistance. So the losses that takes place due to winding resistance is called as copper loss. Now I am audible. Hello. Okay, okay. So kindly draw this diagram. So we have included those winding resistance in the primary and the secondary winding. So let's say if R1 is my resistance of the primary winding and R2 is the resistance of the secondary winding, then I can divide this copper loss into two parts. First is primary copper loss, then we have secondary copper loss. Okay, so the primary copper loss is given by I1 square R1 and secondary loss is given by secondary copper loss is given by I2 square R2. The unit is watts. So the total copper loss will be given by I1 square R1 plus I2 square R2. Okay, so please note this down. The total copper loss and this diagram. So from the above equations 1, 2 and 3, it's clear that the copper loss varies as the square of the currents in the primary and secondary. Okay, so have you understood this, the copper loss? Very easy it is. Once you study, you can write easily in your exam. Can we go to the next point? You have completed this? Okay. Now, other type of loss is iron or core loss. So write down point number B, iron or core loss, which is also called as WI. Notation is WI. Iron losses or core loss. Okay. So let us concentrate in this diagram. So let's say I have my the structure. The base of the transformer is the iron core. It is made up of iron, right? So due to the applied AC voltage, and alternating flux is produced in the core. Agree? Phi is equal to phi m sin omega t. So whenever any magnetic material is placed in an alternating magnetic field, a hysteresis and eddy current loss takes place. That I think you must have eddy current, you must have heard it before, right? So whenever any magnetic material is placed in an alternating magnetic field, the hysteresis and eddy loss takes place. Okay. So the hysteresis and eddy loss takes place inside the magnetic core of a transformer. So this core is iron magnetic core. Okay. So whenever the electric field, I mean magnetic field, gets generated, it leads to a hysteresis and eddy current loss. Okay. So both the hysteresis plus the eddy current loss is my core loss or iron loss. Okay. So this formula. My eddy current and my hysteresis loss is equal to the core loss. So these two losses are together called as core loss or iron loss. Since the core is made up of laminated iron sheets, it is also termed as the iron loss. Okay, fine. Now, the core loss is proportional to the applied voltage. Since the applied voltage is almost constant here, whatever voltage we apply, we are not changing much. So the core loss remains constant for all loads. Agree on this point? You don't have to write all this. You have to write only the main headings. Okay. So any doubt in iron or core losses, they have further classified into hysteresis loss and eddy current loss. So can we go for the hysteresis loss now? Yeah, students. Okay. Now concentrate on this symbol of my transformer. So since the supply to the primary is alternating, your V1 is a AC voltage. Okay, so the core gets alternatively magnetized and demagnetized. Yes or no? Because there's an iron core, magnetic core inside. So whenever we apply a sinusoidal signal, the sinusoidal signal goes positive and goes negative. So whenever it goes positive, the core gets alternatively magnified, and whenever it goes AC signal negative, it gets demagnetized, causing the loss of energy. This is called as hysteresis loss. Understood? So the sinusoidal signal supply voltage applied to the primary is alternating, and due to that the core gets magnetized and demagnetized, resulting in loss of energy. This is called as hysteresis loss. Okay. Now maybe you can write this formula. This loss is given by, you don't have the derivation for this, eta B max raised to 1.6 into F into V. Okay. WH is my hysteresis loss in watts. Here Vmax is the maximum value of flux density in Tesla. F is the frequency of magnetic reversal in Hertz. V is the volume of the material, and eta is the Steinmann's constant. Okay. So how to reduce this cost? Reduce this loss? This loss can be minimized by selecting a material for the core that has low hysteresis coefficient. Okay, so you search for a material which has a lower hysteresis coefficient. Alright? Any doubts regarding hysteresis loss? So if they ask you in the exam, you have to write at least a few points about it. Alright? Can we go to the eddy current loss now? Any doubt? Yes? Okay. Next is eddy current loss. It's a part of your iron or core losses. So this loss is due to eddy current induced in the transformer core. It is seen in the form of a heat. What is the effect of eddy current? It produces a lot of heat. So it is seen in the after effect in the form of a heat in the core. So core gets heated up because of eddy current loss. And this eddy current loss is given by WE is equal to K into B max square F square T square V. Okay, this is eddy current loss in watts, where K is the eddy current coefficient, B max is the maximum value of flux density, T is the thickness of the laminations, F is the frequency of flux reversal, and V is the volume of the material. So you can note it down. You know, that is the reason why we use laminated cores. Here it is. You see, you take laminated cores and join them together instead of a full volume. So this loss is minimized, can be minimized by using laminated core. Alright. Students, you have any doubt regarding eddy current loss? Now a little bit of eddy current. What is eddy current and how it is produced? So whenever a magnetic material is linked with an alternating flux, an EMF is induced in the magnetic material itself as per the Faraday's laws of electromagnetic induction. So this induced EMF circulates a current in the body of the magnetic material. This circulating currents are called as eddy currents. Okay. So these circulating currents, here it is circulating like this. So these are called as eddy current loss. Eddy currents and the losses associated with them are called as eddy current losses. Okay. Understood, students? Because we are now will be changing the topic now. Any query, anyone? What eddy current? It. Acha, okay. WE, this one formula. Okay, it's K into B max square F square T square V. If you remember it, well and good. If you don't remember it, then also it's fine. You have to tell what is the loss, what is the effect of that loss, and how to overcome it. What material you use to overcome it. These 3 points should be there. Yes. Two hours before miss ho jata hai, I didn't get you. From now on, I will be using the same meeting link for all the lectures. This meeting link only. Yeah, why I've given so? Because yeah, I agree. I agree. Just for your information, I'll be using the same meeting link for all the remaining lectures now. Yesterday I have told you the day before that I'll be keeping in the yeah, ठीक है, fine. Yeah. So now we go to transformer parameters. So transformer parameters we will be discussing about winding resistance R1 and R2. We have already seen that. Where is the winding resistance? Here. So if I have a transformer, the transformer windings have some resistance. So this is R1 associated with primary winding. This is R2 associated with secondary winding. Okay. So here we have V1, here we have V2. Both are AC. Okay. Then we have leakage reactance X1 and X2. And then we have impedance Z1 and Z2. So we'll see what are these things, leakage reactance. First we'll go to the primary, the first parameter, that is winding resistance. So just now you have drawn a transformer, or if you have not drawn, please draw a transformer with winding resistance. So here is my transformer symbol. Okay, so the laminated core. So these resistance the resistance which I have shown over here are due to winding resistance. So this is plus minus, this is R2, R1. The current flowing in the primary of the coil is I1. This voltage is V1. This is self-induced EMF, mutually induced EMF, and V2. So this is the diagram for transformer with winding resistance. So please draw it. So we are highlighting the winding resistance. So here let me continue further. R1 is the primary winding resistance, R2 is the secondary winding resistance. So this happens in a practical transformer as there are some resistance associated with primary and secondary winding because they are made up of copper wire. So the resistance of the two windings can be, now here we are having a very important transformation. So have you completed the diagram? Everyone? Okay. Now what I am teaching you, it's slightly important with the for the phasor diagram of a transformer also at different loads. So please listen carefully. So listen to point number 3. The resistance R1 and R2 of the two winding can be transferred to either of the two windings. Okay, does it mean? Let me draw the transformer again. You don't draw it again. Just hold on. So I will draw the transformer symbol. You must have drawn it once, so keep it there. Okay, what we are saying is here, let me quickly write this as V1, E1, E2, V2, I2, R2, R1 and I1. Okay, so what they are saying is the resistance R1 and R2 of the two windings can be transferred either to either of the two windings. That means this can be transferred into as follows. So this R2 can be transferred to primary, or this R1 can be transferred to the secondary winding resistance. So here it is. So when it gets transformed, the diagram changes as follows. So here we have R1 already. Now you have transferred R2, secondary winding resistance, to primary. So it will become, I'm calling it R2 dash. This is R1 actually. So R2 becomes R2 dash when transferred to the primary side. So I'll draw the transformer again. And for the secondary, I'll not show the winding. That gets transferred to the primary winding. Okay. This is V1. This is E1. And this current is I1. Okay. So now it can be proved that a resistance R2 in the secondary is equivalent to resistance R2 upon K dash upon K square in the primary. So what we are saying is R2 becomes R2 dash, which is nothing but R2 upon K square. So whenever you transfer a resistance from secondary to primary, you have to divide that resistance by K square. So R2 divided by K square will be R2 dash. Did you understand this? You don't have the derivation for this, but this is what we have to do. So R2 upon K square. So please draw this diagram, which I am tick marking. Here and this. So you don't have the derivation for it, that it can be proved that resistance R2 in the secondary is equivalent to R2 upon K square in primary. That means R2 dash is equal to R2 upon K square. Completed? Completed the diagram. Can I move ahead? Hello? Students, completed this? Yes. Okay. So the value of R2 upon K square is called as R2 dash. And R2 dash, what is the name of R2 dash? Equivalent secondary resistance referred to the primary. What it is called as? Equivalent secondary resistance as referred to the primary. Alright. So this is basically called as shifting of winding resistance to the primary. So let me draw the diagram again. You don't draw it again, you just wait. So this is R1, this is R2 dash, and this is plus minus V2, E2, I2. No need to draw this diagram again, you have already drawn. Okay. Now these two resistances, are they connected in series or parallel? R1 and R2, R1 and R2 dash. Are they connected in series or parallel? They are connected in series. So these will get added up. R1, RO1 will be R1 plus R2 dash, where R2 dash is R2 upon K square. Okay. So what is this RO2 called RO2 called, sorry, RO1 called as, it is called as the equivalent resistance of the transformer as referred to the primary. Equivalent resistance of the transformer as referred to the primary. Completed? Equivalent resistance of the transformer as referred to the primary. So, we have studied the copper loss. So, what is the copper loss? This current into the resistance. So, it will be I1 square into RO1. So, that will be my new copper loss. Yes? So, why we are doing this transfer of resistance from secondary to the primary? This is for ease of calculations. So, have you written this? Everyone? Hello? Okay. Now, similarly, it can be proved that a resistance R1 in the primary is transferred or equivalent to K square R1 in the secondary. That means now the other way around. Now, if I have the two resistance over here like this, okay, here I have to draw this. So, let's say you have R1, R2, the two resistance. Now, if I want to transfer this primary resistance and shift over here in the secondary, okay, that will be shifted by multiplying K square R1. Okay, so let's do that. This is again the shifting of the primary resistance to the secondary. So here I will have a transformer, plus minus V1, current is I1, this is E1, laminated core. So here this resistance transferred to the R1 gets transferred to the secondary is called as R1 dash, and in series you have R2, the resistance of the secondary winding. So this is V2, E2, and this is I2. Acha, what is R1 dash? K square R1. Are you getting it? So if you are transferring a resistance from primary to secondary, you have to multiply with K square. If you are transferring a resistance from secondary to primary, we have to divide by K square. Got it? And these two resistances together are called as RO2. Okay, so RO2 is called, first of all, R1 dash is called as equivalent primary resistance as referred to the secondary. So RO2 is written as R2 plus R1 dash, which is R2 plus K square R1. And what is RO2 called as? RO2 is called as equivalent resistance of the transformer as referred to the secondary. Equivalent resistance of the transformer as referred to secondary. So please complete this. Have you completed? Okay, someone has joined, I guess. I need to admit them. Please join via Sumaya email ID. I'm admitting now, but still. Okay, now let us proceed with the content. Now we'll go to the second part, that is leakage reactance X1 and X2. Okay, so we have a we have an iron core, of the transformer made up of iron core. Okay, and you have a flux leakage, flux associated with main flux, which is linking the primary and the secondary winding. So in an ideal transformer, it is assumed that all the flux produced by the primary winding links entirely both with the primary and the secondary winding. So this flux, core flux phi, linking between primary and secondary as it is, but that is not the case. Okay, so this is the primary winding, This is the secondary winding. This is the flux associated with distributed between both primary and secondary. So in reality, in a practical transformer, all the flux linked with the primary does not link with the secondary. Okay. So what happens is, I'll show it to you. This is the new diagram. Here, see. Concentrate over here. So I1 is my primary current, I2 is secondary current, V2 is secondary voltage, V1 is the primary voltage. This diagram shows you the magnetic leakage. So as shown over here, some part of primary flux, there is a primary flux flowing phi L1 and phi L2 is the secondary flux. Okay. So as you can see, some part of primary flux phi L1 completes its part by passing through the air rather than around the core. Okay, so there is a gap between the primary and the secondary side, which is the air, hollow air. All right. So the primary flux will be flowing like this, and the secondary flux will be completing its part like this around the air. Okay. So flux phi L1 is called as primary leakage flux. It shouldn't happen. The linking should be very smooth with the primary and the secondary, but we have a flux associated with the primary winding, which is phi L1. So we have a flux phi L1 which is called as a primary leakage flux, which links the primary winding and does not link the secondary winding. Then we have similarly phi L2 secondary leakage flux, which links to the secondary winding but does not link to the primary. And what is my flux phi doing? Phi, which passes through the core, links both the windings and is called as a mutual flux. So phi is called as a mutual flux, linking both primary and the secondary winding. Understood this? Hello? Yes or no? Now, um, this EMF induced, E1 and E2 which is induced, are caused by the main flux. Remember that. E1 and E2 which is produced at the primary and the secondary are called as are caused by the main flux phi. Okay. So this phi L1, which is the flux phi L1, is in the time phase with I1 and induces an EMF EL1 in the primary but not in the secondary. This phi L2 is in a time phase with I2 and induces an EMF E2 EL2 in the secondary but not in the primary. Okay, so you have a flux EL1 and EL2 associated. Okay, hello. So you have a flux called as, because of this leakage flux at the primary and the secondary, you have EMF EL1 EL2 produced in the primary EL1 and produced in the secondary EL2. So the leakage flux linking with each winding produces a self-induced EMF in that winding. So this is equivalent to a small inductive coil in series with each winding. Such, here it is, such that your EL1 now will be given by, so here it is EL1, here it is E1 basically, here it is E2, but due to this current and a small inductive coil, I1 into X1 is called as EL1. This is the flux induced. Okay, this is the EMF induced due to the flux phi L1 and phi L2. And what is phi L1 and phi L2? These are, phi L1 is primary leakage flux and the secondary leakage flux, which I have already informed before. Alright, so here now EL1 and EL2 will be I1 into X, EL1 is I1 into X, EL2 is I2 into X2. So X1 and X2 are known as the primary and the secondary leakage reactance. Okay, so please draw this diagram. This is the transformer with leakage reactance. So basically X1 and X2 will represent the effect of this very important line. X1 and X2 represents the effect of primary and secondary leakage fluxes. Alright, so this will lead to a small inductive coil in series with each winding, and because of that, two more EMF will be induced, EL1 and EL2, which is I1 X1 and I2 X2. I hope it is clear to you. So effectively the X1 and X2 will represent the effects of primary and the secondary leakage flux, which is phi L1 and phi L2. Okay. Can I go scroll down? Hello? Yeah, any doubts over here? Students, do you have any queries? Okay. Now, now please draw this diagram which I am drawing. Transformer with winding resistance and leakage reactance. So the leakage reactance and both we will be showing in the same diagram. So we have R1 over here, small inductor which is X1, representing the effect of primary and secondary leakage flux within the transformer. This laminated core, secondary winding resistance and reactance. Sorry, inductive reactance. X2. Okay, this is X2. This is my V2. Then we have here it is E1 plus minus E2. Here we have current I1 flowing. Here current I2 is flowing. And this is plus minus V1. So this is the transformer with winding resistance as R1 and R2 and leakage reactance as X1 and X2. So please complete this diagram. Okay, completed. Everyone, you all have completed the diagram. Kindly let me know. Yes or no? Okay. Next is impedance. So basically in the practical transformer, as we have already discussed, the winding has some resistance R1 and R2 in the primary and secondary. And also in a practical transformer, there is some leakage flux present near the primary and the secondary. So the effect of primary and the secondary leakage fluxes are represented by reactance X1 and X2. So basically the primary impedance, so this together can be called as Z1. This together R2 and X2 is called as Z2. Okay. So what is my primary impedance then given by? Can you tell me? So Z1 will be given by R1 plus JX1. Why it is plus? Because I know it's an inductor. Instead of writing XL1, I'm writing it X1. Okay. And what is Z2? Can you tell me? R2 plus JX2. Yeah, you can write it. This is basically in the rectangular form. You can write Z1 as or Z1 square as R1 square plus X1 square. You can write it like this also, okay? If you want pure magnitude without any direction. Similarly, Z2 square as R2 square plus X2 square ohms. Unit will be ohms. Agree? Hello? So this is what does impedance mean. Everyone followed or no? Yes. Now we'll use the same funda of shifting. Either we'll shift R1 X1 to the secondary or we'll shift R2 X2 to the primary. So when we shift something to the secondary, you have to divide by k square. And when you shift the secondary to the primary, we have to multiply by k square. That you have to remember. So I will be shifting my secondary resistance to the primary. So So everything will be divided by k square. Can I start now? Are you with me? So I'll be shifting all the parameters to the primary side. So please draw along with me. So I have my transformer now with R1, X1 is the primary winding. Then I have a transformer winding resistance R2 and secondary reactance X2. So this is plus minus V2, this is E2, E1, this is plus minus V1. So this we have to transform the entire secondary resistance into primary, and why we do that? For simplification. So let's start. We'll write R1 X1 R2 dash, it becomes R2 upon K square, right? Then you have X2 dash, which is X2 upon K square. Please complete this. This is V2, E2, E1, and here it is V1. So this is what you mean by shifting of parameters. So we have shifted the parameters to the primary side. So basically we have shifted R2 and X2 to the other side like this. So now it became R1 plus X1, R2 dash plus X2 dash. Okay, all together. So we have shifted all the parameters to the primary side. Okay. Now the same thing, can I write it like this? Can I draw it like this? I've drawn it over here, but I can draw in a better way. It's the same diagram which I'm drawing over here. So you club R and R together, and you club inductives together. So this is plus minus V2, this is E2, E1 plus minus V1. Here we write R1, R2 dash, X1, X2 dash, where R2 dash will be, R2 upon K square. Yes or no? So basically, these two together, R1 and R2 dash, these two together we call it RO1. And these two together we call it XO1. Understanding? Yes or no? So tell me what is RO1? R1 plus R2 dash, which is R1 plus R2 by K square. Understood? Acha, what is XO1? X1 plus X2 dash, which is X1 plus X2 upon K square. Okay. So similarly, the equivalent reactance of the transformer referred to the primary will be XO1. We have written over here XO1. Then the inductance, the equivalent impedance of the transformer as referred to the primary is given by ZO1, which is combination of these two now. This is ZO1, which is RO1 square or RO1 plus JXO1 plus XXO1, or ZO1 will be square root of RO1 square plus XO1 square. Alright? Understanding? Yes, no, what? Are you following? Okay. Now we have transferred primary resistance, secondary resistance into primary. See, now we will next step may transfer primary resistance to the secondary. So let's do that over here. So first it was like this: R1 X1, R2 X2. This is plus minus V2. This is R2. This is V1, I1. So this is R1 X1, R2 X2. Now this gets, you know, so all we are transferring all the resistance to the secondary. So what will happen to them? They'll multiply by k square. So R1 becomes R1 dash, which is k square R1, and X1 becomes X1 dash, which is k square X1. So at the primary side, we get transferred the components to the secondary. So this is plus minus V1, E1, I1. Let me draw it for you all properly. So here we can draw R2. Okay. Instead of X2, I'll write R2 dash. Actually, this will be R1 dash, right? What will be the formula for R1 dash? K square R2. Alright. Then we'll have X2 and X2 dash, X1 dash, which is K square X1. Alright. This will be K square R1. Sorry. R1. This will be K square X1. So please draw this diagram. Over here, this represents RO2. This represents XO2. Why? Because RO1 and XO1 are already taken before. And these two together will called as ZO2. Please complete this diagram. I hope you have followed this. RO2 will be R2 plus R1 dash, which is R2 plus K square R1. That is called as equivalent resistance of the transformer as referred to the secondary. Then equivalent reactance of the transformer as referred to the secondary will be given by XO2, which is X2 plus X1 dash, that is X2 plus K square X1. Alright. So this is the shifting of parameters to the primary side. So the equivalent impedance ZO2 will be RO2 plus JXO2, or ZO2 square will be RO2 square plus XO2 square. Here it is. Alright. So this completes the topic of equivalent resistance. One second. Have you completed? So it's all about parameter transferring from the primary side to the secondary, from secondary to the primary. So first we had R1 X1 in the primary, R2 X2 in the secondary. So first we transferred all the secondary to the primary by dividing by k square. Now we are transferring R1 and X1 to the secondary by multiplying by k square. So R1 becomes R1 dash and X1 becomes X1 dash. Have you understood this concept of shifting of parameters to the primary and the secondary, everyone? Yes, no? Sorry? VO1? ZO1? Acha, ZO1, acha, Z. Okay. Yeah, that depends upon the resistance of the windings and the X2. That depends upon these values, no? Normally, if they are same winding, primary and secondary winding are same, then ZO1 will be equal to ZO2. But if they are slightly different, then of course, yes, this will be different. I'm saying, did you understand the technique of transferring? Okay. So then the last topic for today's lecture, write down, because I'll not take more than 1 hour per day. So we have few minutes left. Let's complete this topic. Write down transformer on no load. So you have this very important, phasor diagram coming up in tomorrow's lecture. Tomorrow mostly we'll cover the lecture around after 4 o'clock, around 4 o'clock. Okay. In a morning slot, I have my oral examination. So in the evening, I will take it around 4 o'clock. Okay. So in the exam, they ask you the phasor diagram, draw the phasor diagram of a transformer in one particular condition. Okay. Or on load, no load, full load. So we are going to study the topic of transformer on no load. Transformer on no load. Can I start with the discussion? If you don't connect anything to the output of the transformer, it is no load. So that means V2 is open. So here it is. Transformer of no load means the secondary voltage is open. Alright. Input you apply, input is the supply. Alright. And I2 is no load. So because of this no load condition, what all things happen? So that is represented by I2 equal to 0. If the secondary current is 0, that means transformer is on no load condition. So a transformer is in no load when its secondary winding is open circuited. That is I2 is equal to 0. So under such a condition, the primary current I1 has to supply for the iron loss in the core and the copper loss in the primary winding only, because secondary has become 0. I2 has become 0. So the loss associated with it, that is I2 into R2, that is gone. So we have to rewrite the formula for iron loss and in the core that will remain same, but copper loss in the primary winding only, that will change slightly. Okay. So the primary winding has some winding resistance. Thus no load primary current. Here we are saying I naught. We are not saying I1 because we are considering no load primary current. I naught lags behind V1 by an angle of less than 90 degree. Why? Why it does so? Because as you can see, you have a resistor and an inductive. Okay, so this primary current, because of that resistor and the reactance, that is a form of an inductor which we have drawn over here, right? Here it is, winding resistance and inductive reactance due to leakage flux. Okay, so with these two, the current instead of I1 we call it I naught because of the open circuit condition at the output. So the primary winding has some resistance. Thus no load primary input current I naught lags behind the V1 by less than 90 degree. Are you understanding? Now the primary, whenever the I2 becomes 0, under these conditions the primary current I1 has to supply for the iron loss and the copper loss both. So the primary current I0 under no load conditions gets split up into two components. So primary current was I1, now it has become I0. So that gets split up into two components. Iron loss component, here it is, IW, and I mu is the magnetizing component. Alright. Now let's see what are these things. Iron loss will be active or a working component. That means IW will be in phase with W1, and IW also supplies for the iron loss. Whereas the magnetizing component, um, I mu is in quadrature with V1. So where phi naught is the phase shift between V1 and I naught 1. Okay. Whereas I mu component is what less? Its function is to sustain or maintain the alternating current in the core. Again I repeat, I mu. This one magnetizing component is wattless. It's reactive power, and its function is to sustain or maintain the alternating flux in the core. All right. So in absence of a output load, I2 is 0, I1 becomes I0, and I0 is IW plus I mu. So here it is, I0 square will be IW square plus I mu square. IW component will be, here you have two components now. See, I mu and IW. Now IW is around somewhere around phase shift of phi naught. Here is my I naught is the resultant current I naught. So current I naught is the vector sum of IW and I mu. So since the main flux is in common to the other windings, your phi can be used as a is chosen as reference power. So from the phasor diagram, since the main flux phi is common to both windings, phi is chosen as a reference phasor. Alright. Now how to draw this diagram? Let me draw over here again. So first of all, have a x-axis in terms of phi. Okay. Next we have V1. Here we have I mu. Okay. Then 90 degrees apart we have I W. Your opposite. Here we have V1 dash. Here we have V2 dash, which is equal to E2, which is equal to E1. Okay. So this is V1 dash. Opposite to is V2. V2 is equal to E2, which is equal to E1 dash. So here IW component is there. That I extrapolate over here, and the resultant current will be I0. I0 dash. Okay. Now why I have written V2 is equal to E2? Because it is so. And why I have written E2 is almost equal to E1? Because all the components are same. So what is phi naught? Phi naught is the angle between IW and I mu, or IW and phi naught is the angle between V1 and I0. So here it is V1 and here it is I0. Okay. So from the phasor diagram, again I repeat, I0 is a vector sum of I0. We cannot add it just like that. It's a vector sum of IW plus I mu. Okay. So this is how the phasor diagram will look like. So V1 is over here, V2 is in the opposite direction, V2 and E2 are in the same direction, which is equal to E1. Okay. Understood this? So from the phasor diagram, the main flux phi is common to the other windings. So phi is chosen as a reference phasor. That's why it is chosen as a reference phasor. So this is the phasor diagram at no load. We are not connected any load. So what will be the no load power input now? No load power input will be V1 I naught cos phi 1, cos phi naught. Okay. So no load power input will be given as Vi cos phi. Okay. So W0 will be V1 I naught cos phi naught, where cos phi naught is the power factor of the load. Now the iron loss Wi will be given by Vi cos phi. Again, here as you can see, the W naught and the iron loss are one and the same thing. So it's V1 I naught cos phi naught. Now from the phasor diagram, also since the flux is common, phi naught, is common to both the windings, flux phi is chosen as a reference phasor. What is phi naught called as? No load phase power factor angle. Write down. Phi naught is called as no load power factor angle. Okay. So yeah, that is all for this topic. I've ended this lecture. So if you have any questions, you can ask, please. I'm open to questions now. Anyone has a query? Okay. So that's it for today.